Okay, hi everyone. I'm Enrique. I'm a second year PhD student. The topic of my presentation today is modeling tectonic crustal deformation with smooth particle hydrodynamics. Sorry, okay, oh, there we go. So we're looking at large deformation problems in geomechanics, which are very common throughout the field. And some of the more immediately obvious ones that one would think of are landslides, slope failures, rock falls, etc. But we're specifically more interested in looking at some geological processes, which also involve large deformation and strain localization and similar features. And this includes tectonics, mountain building on a larger scale, and on a smaller scale, faulting and folding of particular strata or geological layers. If you're interested in looking at large deformation problems in geomechanics and you want to study them, one of the best ways to do it is through simulation or experiments, modeling essentially. And in numerical modeling, you're using a continuum-based approach. You need to know some constitutive model. And if you're above the brittle ductile transition zone in the Earth's crust, it's generally safe to model tectonic crust as an elastoplastic material, which is what we do, or a viscoelastoplastic material. And traditional methods such as the finite element method have been used for modeling some of these processes. But they have some disadvantages when dealing with large deformations such as mesh entanglement or distortion. And although there are workarounds such as like ALE, arbitrary Lagrangian Eulerian finite element method, these are either more computationally expensive or more difficult to implement. And there's also mesh-free methods alternatively, such as the discrete element method, where you have particles interacting with each other through friction and collisions, and you solve Newton's laws of motions for each particle. But this tends to be very computationally intensive, so we prefer mesh-free methods which actually abide by the continuum assumption, such as smooth particle hydrodynamics. And the advantage of mesh-free methods is not only do they not have mesh entanglement or any of these issues when dealing with large deformations, but they also handle discontinuities naturally, essentially. And a third way, which we mostly use as a source of inspiration when studying some of the geology problems we're interested in, is analog experiments using what are called sandboxes, where basically the Earth's crust is modeled as layers of sand, and you scale down all the material properties of the crust to sand. And rather than doing this with sand ourselves, we can recreate this, in our case, using smooth particle hydrodynamics. And if it's a numerical simulation, you have the advantage of being able to detain the simulation and look at some properties which you wouldn't be able to infer from sand, like stress, the deformation, the strain, etc. So SPH is the mesh-free Lagrangian continuum method. And essentially, you have individual material points or particles which represent pieces of a continuum body, and as a result have continuum level properties such as mass, density, stress, velocity, of course. And the way you determine the values of these properties for a particular point is through an interpolation from the neighboring particles within a certain domain. And you use a kernel function for that. And as I mentioned, the advantages of using smooth particle hydrodynamics are related to the lack of issues when in terms of mesh entanglement, dealing well with discontinuities. And it's much more efficient than the discrete element method, which has some of these advantages as well. And you're also working within the continuum assumption, so you can actually specify a constitutive model to your material. So far, it's mostly been used for hydrodynamics. By hydrodynamics, I mean, for example, waves or water. So in a lot of video games and movies, they use smooth particle hydrodynamics to simulate water. And more recently, it's been applied for some geotechnical applications as well. And we've used some of these studies as the basis for our work and for our implementation. So the first geological problem of interest that we're interested in looking at is fault propagation folding. And in fault propagation folding, essentially what you have is what's known as a blind fault, which is located in a layer of bedrock, very hard bedrock, and on top of this hard bedrock, you have some soil or a weak rock. And what occurs is the blind fault will propagate into the weaker material, and you'll get a displacement or offset on the top surface. And this is what it looks like in real life. And as a result, it can be quite hazardous for structures that are lying on top of these faults. The first picture there with the athletic track is from the 1999 Chichi earthquake in Taiwan, which caused billions of dollars in structural damages. And geologists, on the other hand, have been more interested in modeling the same phenomena, but on larger scales. Because what happens is geological strata gets deformed as a result of the penetration of the fault into the overlying weak rock. And you get folding as a result of this fault, hence the name fault propagation folding. And this type of structures are very common in most basin systems, and they're very good petroleum traps in many cases. So that's why we want to get an idea of how they form. And you would also be interested in knowing, for example, if you're drilling into one of these systems or structures, what's the stress and deformation of the material. So we've essentially done two types of different simulations. Some where you are contracting and others where you are extending. And let me show you the extensional case first. So on the left hand, we have these colored layers are simply for visualization purposes. They don't mean anything other than this way you can visualize sort of how the layers are being deformed as a result of faulting that's occurring. And you get what are called horsts and grabens in structural geology in the extensional case, or a scientific conjugate shear bands. And in the compressional case, you get what's known as a monocline and syncline combination. And we're also looking at, for example, what controls the number of shear bands or faults in the weak material layers that we're simulating. What are the angles of these? And so far, we've seen that it's a combination of course, the material properties of the weak rock, the angle of friction, the cohesion, but also the angle of the basement blind fault is critical as well. For example, once it increases past 30 degrees in the extensional case, you stop forming these V-shaped conjugate pairs of shear bands, or what's called a graben in structural geology. And perhaps the other second problem, which is perhaps one of the most studied in structural geology that we're considering, is that of orogenic wedges, which is just a fancy name for mountains, essentially. It comes from the Greek word for mountain, oros. And in this picture here, very simplistic, but this helps understand what the orogenic wedge is. And it's this wedge-like area that forms above convergent margins or subduction zones. And that consists of the mountains that are forming as a result of accretion. And why are they important? Well, they're seismically relevant, of course, subduction zones, and you get famous megathrust earthquakes. And again, there's accumulation of hydrocarbon and other mineral resources in these areas. There's a series of analytical solutions that actually determine the shape or geometry of wedges, and these are known as the critical taper wedge solutions. In the way they measure the geometry of the wedges, if you look at the bottom right hand, that's a simple diagram of what a wedge looks like. You have what's called the basal angle beta, which defines the angle between the base of the wedge and the horizontal. And then you have one called the surface or topographic angle, alpha, between the top of the wedge and the horizontal. And the sum of these two angles actually depends on the internal angle of friction of the wedge, that of the base below the wedge, and as well as the amount of pore fluid that you have within the wedge. And if you plot the topographic angle or topographic slope versus the basal or décollement angle beta, you get this series of fish lobe diagrams in the top right. And within the fish lobe, your wedge is mechanically stable. And that's the point where it basically wants to reach if you perturb it outside of this region of stability. Or if you start from, say, a completely undeformed layer of material, it'll ultimately, if you keep pushing through tectonic forces, you'll reach stability region. Yes. this is what our solutions look like. Some of our simulations plotted against the critical taper solutions. And we're also looking at simulations without cohesion and with cohesion. And in terms of our future work, we're looking forward to incorporating pore fluid, especially in terms of looking at orogenic waters. Yeah, so that concludes my presentation. Thank you.
Okay, thank you. That's not my alarm.
No, that was mine, but I set it slightly off, so I took 10 more seconds.
Okay, Sabrina, it's your turn.
Okay, can everyone see my screen?
Yes.
Yep, okay, so I'll start. So today I'm talking about my current research, which is the effect of saturation-dependent anisotropy in rocks. And so a lot of rocks, for example, shale or slate, they exhibit transverse isotropy in their material behavior. And so depending on the process of deposition, some of them might have bedding planes. For example, we can clearly see stratification in this sample. Or for other reasons, for example, depending on the orientation of the cracks, if they have a preferred alignment, this would result in these rocks having an isotropic behavior perpendicular to the bedding plane. So in this case, it would mean that loading the rock vertically, we would get a different behavior or strain as compared to loading it from the sides. At the same time, a lot of the rocks could actually be partially saturated, meaning that instead of having just one fluid in the pores, there could be multiple pore fluids, which means that we have to account for multiple pore fluid pressures in the same rock. And so the difference between the pore fluid pressures gives rise to capillary pressures or suction stresses, depending on the amount of water or the wetting fluid or the saturation in the rock. And this in turn would affect the permeability and the stiffness and even the strength of your rock. And so we would be able to find a specific relationship between the water content and the suction stress. And so in what kinds of situations would we find rocks that are both transversely isotropic and partially saturated? So a common area is in slopes. So at the ground surface, a lot of the rocks are partially saturated, and depending on deposition processes, some of the rocks could be stratified or laminated, and we would have transverse isotropic behavior. Another one is in tunnel excavation. So during construction, if the tunnel is ventilated, then air could dry out the rock and cause quite high suctions at the tunnel surface. And so this would cause deformation in the tunnel due to drying. And so for rocks that are both transversely isotropic and partially saturated, we would actually have emerging properties based on both of these behaviors or properties. And so mechanically, we actually see that increasing suction or decreasing saturation of the rock would actually increase the stiffness moduli for multiple samples in the literature. And at the same time, we also observe that for quite a few samples that the anisotropy of the stiffness moduli also increased with suction. For hydraulic properties, we also see a similar case where depending on where the horizontal and vertical properties, in this case, the relative permeability, actually differs depending on the saturation of the sample. And so in the literature, there are actually a lot of examples of saturation-dependent anisotropy in both the mechanical and hydraulic behavior of rocks. At the same time, we also see in rock behavior that there is also some strain anisotropy. So in both these cases, the authors performed shrinkage tests where they dried out the sample and measured the strain. And we actually see that there are changes in the strain anisotropy ratio depending on the suction that the rock is exposed to. And so there is also evidence of saturation-dependent strain anisotropy. So the questions I want to pose is, well, specifically, what are the effects that saturation-dependent anisotropy have on a rock's swelling or shrinkage behavior? How can we model that? And specifically, how significant can these effects be? So currently in my model, I've used a linear relationship to express the relationship between the stiffness moduli and saturation, which means that the evolution of the anisotropy ratio is a function of, is a ratio of the two linear functions. And we can see that for some samples in the literature that actually a linear relationship can actually be a good, is good at showing what the relationship between the moduli and saturation are. And for the permeability and anisotropy, I've used a log linear relationship, which actually has been shown as a good fit for sands and some other soils. So currently what I've done is I've used finite element modeling to simulate a shrinkage test on boom clay, which was done by Prime and coworkers. And so I've used a quarter cylinder mesh and applied different suction values to it for different material properties, with cases where we consider saturation, for cases where the material properties are independent of saturation and where they do depend on saturation. And so we can see that if we do not consider saturation dependence in the material properties, the strain anisotropy actually stays constant throughout the suction as expected, but then we would not be able to replicate measurements from the literature where the strain anisotropy actually increases with suction for certain soils, for certain rocks. And at the same time, for different, for the strains, when we look at the strains, we actually see for this case where an increase in the suction would actually have increasingly different strains predicted depending on whether you consider saturation dependence of the material properties. And so this actually might imply that we could be over or underestimating the strain at high suctions if we do not consider saturation dependence. So in closing, so my current work is focusing on saturation dependent anisotropy, and I have currently shown that strain anisotropy that has been measured in the literature can be explained by having stiffness anisotropy in the rock behavior. And moving on, I will be doing further work on the effects of saturation-dependent permeability anisotropy. Thank you. Okay.
Okay, thank you. So just a reminder, if you want to ask any question, just feel free to send them to me via chat.
Wait, how do I?
Wait.
My screen. Hello?
Yes.
This is my screen. Okay, how about now?
I can just see black and white horizontal bars.
Yeah, because I'm sharing it now. So can you see the full screen now? And
Go ahead. Go ahead.
Okay. Hi everyone, I'm Wei Chen, and I'm a second year PhD student under the guidance of Professor Bohan. It's really nice to meet you today. I will talk about the chemohydromechanical modeling of the impacts of carbon dioxide on shale behavior. It's knowing that the behavior of shale is important in industry, like in petroleum engineering. Before looking into the impact of carbon dioxide, let's look at the modeling of shale, ignoring chemical effect first. As I stated, the importance of shale behavior inspires many researchers to do modeling of shale. Very good modeling of shale has been developed by researchers. For example,
excuse me, Wei. We can only see horizontal lines. There is
horizontal line.
No, we don't see any image. There, yeah.
How about now?
Yes.
Now you can see it, right?
Yeah.
Okay, maybe I I will not go into the full screen mode. So I'll continue here. Okay. Before looking into the impact of carbon dioxide, let's look at the modeling of shear ignoring chemical effect. As I stated, the importance of shear behavior inspires many researchers to do modeling of shear. For example, right in our group, many researchers have done awesome work about shear. For example, Zhao Yang, Zhang Qi, and Yin Qing. They will give presentation later. Okay, from my point of view, the three main factors we need to consider for modeling shear are anisotropy, double porosity, and viscoplasticity. Shear is a kind of sedimentary rock, so that it is usually assumed transverse isotropic. Sabrina just introduced what is transverse isotropic, so I will not go deeper here. It means that the behavior of shear is different in bedding normal and bedding parallel direction. Here, both the fluid flow and the mechanical behavior will be assumed transverse isotropic. Of course, their bedding normal direction could be different. Therefore, our elastic modulus and permeability tensor will have a transverse isotropic pattern. Besides, there are pores of different size inside shear. We need to differentiate different pores. The popular models we use now is double porosity. The pore is categorized into different scale. Finally, we want to describe shear with viscoplasticity theory. If you are not familiar with this, don't worry. Someone later will give the presentation about the viscoplasticity theory. Our group actually has proposed a very effective anisotropic chemical plasticity model, which is suited to use here. Of course, shear has other important properties like heterogeneity, but let's just focus on the above three factors first, because these three are closely related to the carbon dioxide impact. Okay, just as I mentioned, the three main factors, anisotropy, viscoplasticity, and double porosity, are important in shear modeling. This is actually gives us a hint to research on the impact of carbon dioxide on shear. We start from the property of shear. For anisotropy, we have assumed that shear is transverse isotropic. So there are 5 independent elastic modulus, the Young's modulus and the Poisson's ratio on the bedding normal and bedding parallel direction, and the shear modulus on bedding normal direction. Also, the fluid flow is also considered transverse isotropic too. Given that we assume double porosity, we have 2 scales. So now we have 4 independent parameters to describe permeability tensor for different pores of scale. The double porosity also inspires us to study the volume ratio of pores of different scale. So we need these 3 parameters to describe the pore volume ratio. For the plasticity model, the surface energy decrease caused by carbon dioxide absorption results in cohesion softening and reduction of shear strength, which will influence the plasticity model here. So now you know these parameters or factors are important in shear modeling. I will show you that carbon dioxide will influence all the content here later. Let's look at how the carbon dioxide reacts with shear. We know that shear contains calcite and dolomite, which could react with carbonic acid. Given an acid environment, we end up with a solution with calcite ions, magnesium ions, hydrogen ions, and carbonate ions. So we have a chemical reaction balance now. See, if we inject carbon dioxide here, we will facilitate the reaction of the reverse direction, which will reduce the content of calcite and so on. Interesting. The stiffness and strength of shear depends on the content of calcite and so on. Of course, the acid environment also dilute organic matters. Lastly, recall the basic chemistry. It tells us that the chemical reaction speed is different due to different contact area, which means that the impact of carbon dioxide on shear could be heterogeneous across different areas. Okay, now let's look at the impact of carbon dioxide on stiffness and strength. carbon dioxide could dissolute calcite and so on, so that the phi elastic modulus here changes. We also note that the chemical reaction speed is different across different areas. The heterogeneous chemical reaction gives rise to the different reduction of elastic modulus. For example, the experiment showed that shells with parallel and normal bedding angles exhibited reduction in the value of Young's modulus of different reduction under a certain condition. More trickily, experiment shows that the elastic modulus decrease with carbon dioxide saturation and then increase. This is due to the competing effect of solid dissolution, saturation pressure, and swelling. Carbon dioxide induced swelling is due to the decreased surface potential energy of shell with carbon dioxide absorption. It results in increased porosity with an effect that is similar to that of solid dissolution. So it tends to degrade the stiffness of the solid. However, the increased saturation pressure tends to increase the stiffness of pressure-sensitive materials, such as shell. So there is a competing effect here. Besides, the strength of shell reduced because of the effect of carbon dioxide absorption. The curve also decreased first and then increased. To assume, we could conclude that both strength and stiffness decrease, although there is a small bounce back. Same for permeability. Chemical reaction cause the void volume ratio to be larger. However, the difference of chemical speed results in different increase of void ratio for pores of different scale. We could conclude that in general, the pore volume ratio becomes larger. When modeling the evolution of permeability at the continuum scale, a power-law relationship between permeability and porosity is usually assumed. So the four permeability parameters here becomes larger due to larger pores generally. But the chemical reaction speed is different. So the permeability variation is also different in bedding normal and bedding parallel direction for pores of different scale. Okay, till now, we know that we need to propose a constitutive model to simulate solid dissolution. You know, the variation of these parameters and how they could be related to the traditional hydromechanical modeling of shell. And we just need to propose a new constitutive model and include it in the traditional hydromechanical framework. I'm not going deeper here to save more time. What's more, we know that the source of carbon dioxide impact is the dissolution of calcite and dolomite. The dissolution distribution also matters. The reaction speed is different across different areas. So we could do a carbon dioxide saturation experiment to observe the microstructure characterization before and after carbon dioxide treatment. To summarize this research, we know that carbon dioxide could facilitate the dissolution of calcite and dolomite in shell. The dissolution of calcite and dolomite caused the reduction of stiffness, strength, and increase of permeability. So we want to propose a new constitutive model to describe a solid dissolution, and we want to include it in the traditional hydromechanical modeling framework. Finally, to provide experimental contrast, we also want to conduct a carbon dioxide saturation experiment. That's all for my presentation. Thank you.
Okay, thank you, Wei. So Julia, you're next.
Let me share my screen. Oh well. Okay. Can you see my screen?
Yes.
Yes, nice. So I'll start. I guess I'll start with a broad introduction, but I suppose everybody already mentioned what I'm going to say here. So my research aims at improving our understanding on how geological materials behave And for that, I use numerical methods. So I'm particularly interested in the hydraulic and mechanical behavior of those materials and how they interact. And that's why we need couple simulations. But couple simulations come with many numerical challenges, and during my PhD, I tackle some of them. But before mentioning them, I wish to motivate why it is important to study this coupled behavior. So geomaterials are deformable, meaning that if we apply a load on one of its face, the material will change its shape. That's what we are seeing here in this figure, where we have a CT image here of a soil sample. And we can see how it deformates, it changes shape as the triaxial task goes on. So geomaterials such as rocks and soils, they are deformable and they are also porous. And within their pores, we have fluids, which can be multiple fluids, water, oil, gas, and so on. And they flow within the pores. And we can see how here in this image, how this sample here is initially saturated with the gray fluid, oil, and how the water displace this oil and slowly saturates the sample. What is fascinating about geomaterials is that this mechanical and hydraulic behavior, they influence each other, and they are the cause for a variety of issues in geosciences. For example, here on the left, we see how the soil has sank by several feet, and this was only due to the draw in the area. This picture was taken here in California at the San Joaquin Valley. And in the other side, we see an image of a landslide, the La Conchita landslide, that caused the death of more than 100 people. And we know that water weakens the soil strength. And so we can see how here, and this landslide happened after a very heavy rainfall. And we can see here how these two behaviors, they are tightly related. We have solid deformation and fluid flow tightly related. So we have ways of predicting those events through modeling those events, and we need couple simulations for that. During my PhD, I've tackled mostly three challenges. The first one is related to the method, the discretization method that we choose for solving our problem. We use a finite element, finite volume discretization, and this discretization, unfortunately, is not intrinsically stable, meaning that under certain conditions, we'll have oscillations showing up in our solution that are not physical. Then I looked into the performance of iterative linear solvers and how to speed up, in a way to speed up our simulations. And finally, I've used the proposed numerical framework to study the deformation that would arise due to injection of fluids on an offshore carbon storage site. So I'll show here the results for the first two parts. In this first part, the macro element stabilization, we'll see how it will treat the spurious oscillations that appear. Here, this example shows a unit square where at some point we are injecting fluid in the domain. So those oscillations that appear when our fluid and solid constituents are close, are nearly incompressible, and our simulation is close to undrained conditions. So that is why we are simulating only one time step, a very small time step, and our permeability is also very small. So in this case, when we apply here a pressure, we'll see that for our finite element, finite volume discretization, our result will look like that if we don't have any stabilization method. So we can see after developing our proposed stabilization and implementing it on the code, we can see that here we have our results, that is the expected result. Everywhere we have a zero pressure. At the very beginning of the simulation, the pressure is zero everywhere except at the point where we are applying the pressure. So we can see how the stabilized formulation treats the spurious oscillation in that case. The second part is related to the performance of iterative linear solvers. So solving the linear system of equations that arise takes most of the computational time. So let's look from where these linear system of equations, from where do they come from? So here is a basic setup for nonlinear code. Our simulation is transient, meaning that we'll have to go through a non-linear loop for every time step. Within this loop, we'll have to discretize our equations. We'll get a non-linear residual that we would want to drive it to zero. For that, we use a Newton-like method where we have to assemble our stiffness matrix and our residuals. And then we'll have to solve this. This is our linear system of equations. We solve that, we update our solution, check for convergence, and if it hasn't converged, then we go back to this loop. So we can see that if we would like to speed up our simulations, we have to find ways to speed up how we are solving this large linear system of equations. We have broadly two ways of solving this large linear system of equations: through direct methods or iterative solvers. Direct methods are very robust and they will get you to a solution even though your Jacobian coefficient matrix A is ill-conditioned. The problem with direct methods is that they are very memory intensive, and some might even say that it becomes generally computationally infeasible to solve a 3D problem, a large 3D problem with a direct method. So another alternative is to use iterative solvers. They need less memory, they have more scaling capabilities, but their efficiency is tightly related to the conditioning of the Jacobian matrix. And that is why we need good preconditioners for them to be effective. Preconditioners, they are better, if they are more efficient when they are better suited to the problem, the underlying physical problem. And when we have strong capillarity effects on our system, we can see that capillary influences how the saturation variables will evolve. So we can see here, for this case, we can see that saturations are more diffusion dominated than for this case here. And here we are only changing the capillary model from one simulation to the other. So the objective of this work was to design preconditioners that are suitable to the strong capillary regime. And to test the three preconditioners we have designed, we tested that in the simulation here. This is a highly heterogeneous domain. Here we can see the permeability of the domain, and it is initially saturated with oil, and we are injecting water here at the center of the domain, and we may produce both fluids at each corner of the domain. So we run that simulation and for several cases where we only change the capillary model, which has this form here. We can see that as this Pmax grows, we'll see that the diffusion of saturation variables will also grow. And so here are our results. We can see here for a larger Pmax how we have a more diffusive saturation variable, and this will influence our displacements. But what we are interested in is how our iterative linear solver perform. And we can see when we have larger Pmax, larger capillary pressure effects, we can see that the base case, the preconditioner that we use as a base case, it takes many more iterations than the other two variants that we are designing to better handle strong capillary effects. And this directly translates on the timing for the simulation. In blue is how long our linear solver is taking for the base case scenario. And we can see that it grows as the capillary effects grows. And the other two strategies we have designed, they have the opposite pattern. So this is my research so far. Thank you.
Okay, thank you, Julia. Next is Yang.
Okay, can everyone see my screen?
Yes.
Okay. Hi everyone, I'm Yang, a fifth-year PhD student working with Professor Borja. Today I'm going to talk about my recent work on hydromechanical modeling of coupled solid deformation and fluid flowing shale. Shale is a typical sedimentary rock that has laminated structure. As you can see in the left figure, in the shale sample, there's apparent bedding plants resulting from sedimentation and diagenesis processes. If we zoom in a little bit using X-ray topology imaging technique, we can see minerals, particles, and microcracks aligned along the preferred bed parallel direction. Laminated structures in shale will influence both shale's mechanical behavior and transport properties. As revealed in the left figure, rock strength of shale is dependent on the bedding plant orientation embedded in the test sample measured in conventional triaxial compression test, exhibiting a U-shaped variation curve. In the right figure, it's a relationship between permeability and porosity of shale. As you could see, given a certain porosity, permeability along the bed parallel direction, marked as a solid spot in the figure, will be orders of magnitude larger than permeability along the bed normal direction, marked as a circle in this figure. This is also resulted by the microcracks aligned along the bed parallel direction. Meanwhile, shale is also a very ductile rock that could undergo large inelastic deformation. Faced with those observations, my objective is to develop a continuum framework for coupled solid deformation and fluid flowing shale that considers material anisotropy and uses plasticity model to capture the inelastic deformations in shale. In my formulation, shale is idealized as a transversely isotropic material, which could be characterized with planes of transversely isotropy and also the normal vector. The microstructure tensor defined here will be an important tensor to characterize the anisotropic mechanical behaviors of shale. The equations we're solving for in this formulation are the balance equations of mass and linear momentum for the mixture of solid.
I've got a question for you. What if you could watch all the CCO news you...
Okay, and what's unique in our formulation is that since we're using an elastoplastic solid skeleton, the strings will decompose into elastic component and plastic component, and they have distinct contributions to the mass balance equations. As you could see, there's a B tensor in front of the rate of elastic string rate. And this B tensor is further evaluated in our derivation as functions of the elastic tangent modulus of the solid skeleton and also the bulk modulus of the solid constituent. For transversely isotropic materials such as shale, this formulation could be simplified with only two B coefficients along the bed normal and bed parallel directions together with the microstructure tensor. Another important aspect in a coupled problem is the identification of effective stresses. In our formulation, we identify two distinct effective stresses for elasticity and plasticity respectively. For the effective stress for elasticity modeling, the pore pressure term is scaled with the Biot tensor, while for plasticity modeling, the effective stress is in the form of Tersagi's effective stress. As for the constitutive modeling for solid deformation, we use the anisotropic modified Kamm-Clay model after Simnani et al. And Zhao et al. Finally, for fluid flow through porous space, we use Darcy's law, and we use this anisotropic permeability tensor, which is also characterized with the two components along the bed normal and bed parallel direction, together with the microstructure tensor to capture the anisotropic behavior. Okay. Next, I'm going to show an example of the application of the proposed framework, where we investigated a consolidation problem of transversely isotropic elastoplastic medium under a strip loading. For this investigated domain, the bedding plan orientation is 45 degrees, and this domain is also under an overburden loading to be 1 megapascal. The strip loading is also 1 megapascal. We use 3 different material models, including an elastic material and a normally consolidated shell where pre-consolidation pressure to be 1 megapascal, and then over-consolidated shell with an over-compression ratio to be 2. We will report the ground settlement as well as the evolution of pore pressure at point A here. As you can see in the left figure, it's the evolution of pore pressure after the strip loading has been applied. As you can see, the pore pressure will build up initially and then dissipates during consolidation. For normally consolidated shell, the initial buildup of pore pressure will be largest because it's the weakest material and it takes time to consolidate and get stronger. So after the strip load has been applied, most of the external load will be carried on by pore pressure. In terms of ground settlement, the media made up of normally consolidated shell will undergo a largest immediate settlement as well as consolidation settlement. And the media made up of elastic material will undergo least settlement. Next, we reported contours of pore pressure after 0.6 days of consolidation. The left column is a comparison result generated with an isotropic media, while the right column results generated with the anisotropic media. As you can see, the contours generated with the isotropic media will be symmetric along the vertical center line. However, when anisotropy were accounted for, the distribution of pore pressure will be skewed. And the rows corresponds to elastic materials, normally consolidated shell and over-consolidated shell. For the first two materials, pore pressure distribution are light bulb shaped. However, for over-consolidated shell, the contour of pore pressure is an arc shaped. Finally, we want to show the contour of plastic strain at the end of the consolidation. As you can see, for normally consolidated shell, we observed a cone-shaped localized plastic deformation, while for over-consolidated shell, we observed conjugated localized plastic deformation bands. If anisotropy has been considered, the preferred direction of the localized deformation band will be along the bed normal direction. That will be all of my presentation, and the other details could be found in my paper. And I would also like to share a photo of my newborn daughter, Demi. I don't know, I haven't shared the news with all of the group members, and I want to share my happiness and my joy to every one of you. Thank you.
Congratulations, Will Young.
Congratulations. Well, the next presenter is, or the next speaker is Chi, but he just told me that he had to go to a dentist for root canal, an emergency treatment, but he left a video of his presentation. So I'm going to play that video for you.
Hello everyone, my name is Qi Zhang and I'm a graduate student working with Professor Broha. Today I'm going to give an overview of my research, which is fluid flow through anisotropic and deformable porous media with ultra-low matrix permeability. So I will divide my today's presentation into 5 parts. So let's go to the first part, the mathematical formulations. So first of all, we need to know the basic assumption of double process theory, which assumes 2 superimposed grids in space. In other words, for one physical point, there are 2 pressure values, one representing the average pressure in the fracture network and the other in the matrix pores. And here, I will use subscript 1 and 2 to represent the matrix pores and micro cracks, respectively. So this flowchart gives a brief overview of the mathematical derivations of these formulations. So basically, we start from the mass balance equation, and by simplifying the right-hand side, we obtain the momentum balance equation. And then by eliminating some terms, we get the energy balance equation. And in order to obtain a postulate some constitutive laws, which is represented by these arrows. So the first constitutive law is modeling of the process change with time. And here I have provided 4 approaches. So the first one is the phenomenological approach, which means that we will generalize from single process equation of d phi dt. And the second approach is based on the principle of superposition. And the third approach is the Betti's reciprocal theorem. And the last approach is the Berryman's approach. So for all the approaches, we require that they should be consistent with the single process equation when either phi1 or phi2 vanishes or p1 equals to p2. So the second constitutive law is the Darcy or non-Darcy flow. So for flow in macro cracks, we assume the flow will follow the Darcy's law with full permeability tensor K2, which I will talk in the next part. And for the flow in matrix pores of some unconventional reservoirs, we assume it will follow the low velocity non-Darcy flow, which is represented by this figure. So in this figure, we can see that the non-Darcy flow can be divided into 3 segments: the no-flow segment, the nonlinear segment, and the linear segment, separated by the threshold gradient lambda minimum and the critical gradient lambda maximum. And you can see for a given gradient, the Darcy velocity calculated by the non-Darcy law is always smaller than that using Darcy's law, which is a basic characteristic of low velocity non-Darcy flow of liquid, resulting from the interaction between the fluid particles and the solid. And this non-Darcy flow will also affect the mass transfer by decreasing the leakage parameter gamma. And you can see from this figure, if the gradient is less than the critical gradient, then the leakage parameter will decrease from its maximum value. So the second part is the equivalent fracture permeability. So here we adopt an upscaling approach based on the flow rate. That is to say, we will run a model with explicit fractures sketched here. And we can simulate it using either the discrete fracture model or embedded discrete fracture model to get the flow rate. And then we can calculate the flow rate from a continuum model. And by equal these 2 flow rates, we can get the equivalent fracture permeability. And so the third part is scaling analysis. Basically, we want to quantify the impact of mass transfer in the solid deformation equations. So to achieve that, we will define some characteristic quantities, and then we will calculate the dimensionless number as a function of pressure variations delta P and delta PD by assuming practical values for permeability, density, viscosity, and shape factor. And as a result, we can see that for almost all the cases, we can ignore this term without losing any solution accuracies. So in the fourth part, I will give an example. So how to solve the Gaussian equations? So the first category is known as the analytical method. Basically, we can try separation of variables, which you need to know the Strum-Liouville theory, and you can also try the Fourier transform, the Weber transform, the Hankel transform on the space domain. And you can also try Laplace transform on the time domain, which will also require some knowledge of complex analysis. And the second category is known as the numerical method. For example, you can use the standard finite element method to solve the deformation equation, and the standard finite element method to solve the flow equation. But the problem is that this is not mass conservative. So therefore, people will have proposed some better methods, such as mixed finite element method or finite volume method. And the finite volume method is best for the multi-phase flow problem with zero capillarity. And in addition, for some 1D problems, you can try the finite difference method, which is much more easier to implement. And the last category is some machine learning or deep learning methods, such as Gaussian process and deep neural networks. So here, I give a typical example, which is a 3D compression problem. So we have applied the load on the spherical surface, which will generate the axis pore pressure in this saturated porous medium. And also the saturated porous medium is assumed to be transversely isotropic with horizontal bedding planes. And some key parameters are summarized here. So we assume the equivalent fracture permeability is highly anisotropic, which means that the vertical component is much smaller than the horizontal component. And we also assume the non-dartless flow exists, and the external load F is a function of the spatial coordinate X. So the axis pore pressure dissipation process is shown here. So from the first row, we can see that the spatial distribution of P1 is dependent on the external load F, because it is the fluid in the primary porosity that supports the large portion of load in the beginning. And for P2, we can see that even though our equivalent fracture permeability is anisotropic, it will not skew the pressure distribution, which is because our plane of isotropy intersects with the boundary conditions, which will lead to a horizontal preferential flow direction. And also you can see that in the beginning, the difference between P1 and P2 is large, which means that the non-equilibrium flow will appear as soon as we apply the load. And as time goes on, you can see the difference between P1 and P2 decrease, and also the porous medium is compressed. And at the last time step, you can see the distribution of P1 and P2 are almost the same. So finally, I will conclude my presentation. So here I have proposed a comprehensive global porosity framework, which includes multi-field coupling and various flow patterns. And secondly, I have proposed a simple upscaling approach to calculate the equivalent fracture permeability. And thirdly, under reasonable ranges of material properties, we can ignore the mass transfer term in the deformation equation. Therefore, a practical framework is available. And finally, we have used the 3D micro example to demonstrate the characteristic of hydromechanic responses of double porosity media. And that's all about my today's presentation. Thank you for your listening.
Okay. Did you hear Chi? I forgot
Yeah.
to ask you if you.
Yeah, I can hear.
Okay, so next is Will.
Can everybody see it? No. Let me reshare it. What about now? I think it works.
Yes.
Okay. So my today my name is Yin Qing. So my you can call me Will, and today I'm going to talk about my work on the creep of shale from nanoscale to specimen scale, advised by Professor Bohar. First, I would like to introduce the concept of creep. So creep is a time-dependent deformation of material under a constant stresses or loads. A typical creep stream versus time plot is shown here. So at a certain time, we apply a constant load, and the material along that direction will undergoes elastic deformation immediately. And after that, as time goes, it will go through 3 stages of creep. First is the primary stage, that you have a decreasing strain rate, and then you enter the stabilized stage, which is also called secondary stage. You have a very constant creep rate, and sometimes material will enter the third tertiary stage, where failures like shear bands or fractures will happen. So generally, experimental researchers uses 2 experimental methods to study the creep behavior of a material. First one is the traditional triaxial creep test. They use a UMT machine here. It can add confining pressure to the material, and then add actual loading along the axis of this cylindrical sample. After applying this loading, they record the creep strain along this actual direction as a function of time. And this example is on the Eagle 4 shale. We can see that the creep curve, first of all, the observation is the creep lasts for like 10 to the 4th hours, which is almost a month. This is a very time-consuming experiment. And secondly, the experiment first load the material and then unload it and then reload it. After this load and reload procedure, every time we can see a residual viscoplastic strain here. So which means this behavior is viscoplastic. Another method that has been recently developed to study the creep behavior is called nano or micro indentation test. In this test, researcher using a very hard indenter, say a diamond indenter, to indent into the material. And the indentation test always mostly have 3 stages. First is the loading stage, and then the researcher maintained the loading for a certain time. After that, this maintaining stage is when creep happens in the material, and after that, they load it. Depending on the indentation depth, the indentation test can be characterized into nano and micro. Say, for example, if we only indent into the material for several or hundreds of nanometers, normally we will only engage one material phase in the material. And if we indent to several micrometers, then normally we engage a mixture of several components. So in the creep test in another indentation, the creep behavior normally only lasts for several minutes to achieve the same stage of the second steady state as in the as in the triaxial creep test. So our goal is to predict this long-term creep behavior of the large sample, say in the centimeter scale, directly from those indentation tests in the nanometer and the micrometer. So how can we achieve that? There are two ingredients, actually three. We need nano indentation tests in the lab. And second, we need a constitutive law to describe the shale rock. And thirdly, we need numerical simulation method to simulate the indentation test and then calibrate the material properties. Using those material properties, we can simulate the triaxial creep test in the larger scale. So the first ingredient needs us to look close at the material at multi-scales. As has been introduced before, this shale is multi-scale heterogeneous and multi-scale anisotropic. At the submicron scale, we can see that the shale sample has different compositions like quartz, feldspar, and carbonate. And we also have the organic matters. Here we can divide the materials into two phases. One is the hard phase, which means the material are very hard in terms of their elastic Young's modulus. And we also have the softer materials, the organics and the clays. They are the major contribution to the creep behavior of shale. So we, under this assumption, we can divide the materials into two components, and we have this constitutive law that has two different material phases representing the mixture of shale in the submicron scale. So the hard phase and the soft phase both have their separate volume fraction. In here, this volume fraction sum to 1, and both phases are viscoelastic. But since the soft phase contributes most to the creep behavior, soft phase has a much lower viscosity, and then hard phase has a larger viscosity. So now we have the constitutive law. Next, we need a computational framework. So here we use the numerical method using the finite element method. We develop an in-house finite element code called GeoScale. This code can simulate nano indentation, micro indentation, as well as triaxial tests with heterogeneous mesh. Notice that the challenge in the indentation simulation is the computational cost. Normally, when you have a contact problem in 3D, the computational cost is going to be your main challenge. And here we use some techniques to reduce the cost and model this Berkovich shape. It's actually a tetrahedron. And when you have a tetrahedron that is indented into a material, you will have some singularity around the tip area, say here. So we also need to resolve that. So after resolving those problems, we can do this indentation test in 3D and calibrate the material properties of both the hard and soft. And then we can conduct this triaxial creep test in 3D as well with a heterogeneous mesh. Let's see this framework work in action. So here is one of the examples to conduct the indentation test. So we first, this is a 3D test, but I plotted in 2D. This is the eagle plot. And we first load it to a certain loading. Say here, I think is around 3 micronewton. And then we hold the load. We can see that the material is further indented downwards, even we hold the load. And then we unload this material. So we can see the result of the indented residual compared with the experimental result. It's very close. Then after this, we can use the calibrated material to model a triaxial creep test. And this is the predicted curve that we have seen. This time is in 10 hours. It's not in months, but it's still very long compared to indentation test. That's all. Thank you. Ronnie, you are muted. Right.
I said, you have misspelled my first name badly. I will not forgive you for that.
Really? I said Professor Ronaldo.
Anyway, the final speaker is Jimmy.
Can you hear me? And can you see the
Yes.
PowerPoint? Hello, everyone. I'm Ying Xiao, and you can call me Jimmy. Today, I'm going to give the presentation on my research about the contact algorithm for modeling 3D indentation experiments. Let's begin with an introduction. Shale is a highly heterogeneous material composed of hard crystalline aggregates and soft matrix of clay and organic matters. It exhibits strong viscous creep behavior, which is an important factor in the assessment of land subsidence and wellbore stability. Traditionally, the creep of shale is studied in the triaxial creep test at the centimeter scale. However, the triaxial creep test has three main drawbacks. First, standard intact samples with the size of a few inches are required. For shale, its chemical and mechanical instability makes recovering cores expensive or even impossible. Second, triaxial creep tests are time-consuming. They typically last for days, if not months. Third, triaxial creep tests are designed to measure the creep properties of the shale mixture at the centimeter scale. It is not possible to study the mechanical processes at the mineral component scale. Recently, with the advance of technology, creep behavior of shale samples can be studied through indentation testing. The apparatus is shown in the figure. A hard tip of known geometry and mechanical properties, which is also called the indenter, is pressed into the sample. Both the applied load P and the displacement of the indenter H are recorded. The underlying rationale is that the contact response of a material can be used to determine its bulk mechanical properties. The indentation test usually involves three different stages: the loading, the hold, and the unloading stage, which can be seen in this pH curve. And we can notice that during the hold stage, the load is kept fixed, but the sample continues deforming. This is where the creep properties of shale are measured. In order to model the indentation test, we need to know about the contact mechanics. Let's consider the contact between two bodies, omega-1 and omega-2. We name one side of the contact boundary as the master side and the other as the slave side. For one point x2 on the slave side, there is a point x1 bar on the master side by projection. The initial gap between x1 bar and x2 is G0. This pair of points is said to be active if the contact happens here, and their displacement must satisfy the first equation, meaning that there's no gap left, and there can be a negative contact traction at both sides of the contact surface. If contact doesn't happen here, this pair of contact points is inactive. There should be a gap left, but the contact tractions on both sides are zero. The above two cases can be summarized in the general contact condition, which is also called the KKT condition. If we denote the negative of the normal component of the contact traction as lambda, then the contact condition for both the active and the inactive cases is shown in this equation. However, the contact mechanics has the two main challenges. First, the first challenge is how can we discretize the two bodies on each side of the contact surface. The second challenge is how to detect which part of the boundary is active and which part of the boundary is not active. This is what our algorithm solves. First, the discretization of the two bodies or the meshing part. In literatures, there are two ways. One way is to create two meshes that match each other at every single node along the contact surface. The second way is to create two non-matching meshes. For the matching case, the contact is node to node, and it is easier to formulate the matrix form, but it will take a lot of effort to create the meshes, especially if the two bodies are of irregular geometries. For the non-matching cases, we can create it's very easy to create the two meshes, but special mapping techniques like the node to surface, surface to surface, or multi-element method must be used to determine the contact pairs and the contact forces. Also, both the matching and the non-matching schemes suffers from the convergence issues if one body is significantly stiffer than the other, because then in the system matrix, we will have a block of very large values and a block of very small values, which makes the system poorly conditioned. So instead, a new discretization scheme is proposed here, where only one body is discretized, the sample. For the rigid indenter, it is modeled as a single degree of freedom. The underlying concept is that we only need to know the position of one point in order to know the position of the entire indenter. We do not care about the actual distribution of the contact force for the rigid body, so we can just transfer the distributed contact pressure acting on the rigid body into a concentrated contact traction applied at a single point. This contact algorithm actually becomes a single node to entire surface contact. In order to determine which part of the boundary is active and which part of the boundary is inactive, we use the active set method. Without this method, the common way is by trial and error. That is to say, we assume a non-active contact boundary outside the Newton iterations. We solve the system of equation for this assumed contact condition, get the solution, and then check whether the solution is valid for the assumption or not. If not, we need to assume a new content and repeat. That is to say, at least two nested loops are required. In comparison, for the active set method, it combines a contact check into the outer Newton iterations. During each Newton iteration, the method checks the following condition to determine whether this pair of contact is active or not, and update the active set accordingly before the next iteration. So the two nested loops has been simplified into a single loop, and in practice, the exact active set at each time step can be determined with only 2 or 3 trials. After introducing all the important parts, we have the overall algorithm summarized in the box below. Finally, let's look at some numerical examples. The first example on the left demonstrates the efficiency of this algorithm dealing with 3D indentation simulations. Traditionally, the meshes for the sample block and the indenter must be highly refined in both the matching and the matching scheme. Otherwise, the solution may not converge, or the result may be highly inaccurate. This is required by commercial software like Abacus, and the model is shown in the top left figure. In comparison, for this algorithm, a simple model is shown in the bottom left figure is needed. The rigid indenter can be matched without any further refinement. The reason why we will have a few elements for the indenter is that the program only supports 8-node cubes rather than 4-node tetrahedron. And the table below shows the detailed comparison. If we simplify a model where the element size of the indenter is approximately the same as the element size of the block to the model on the bottom, we actually reduce the number of cells and the number of degree freedoms by 1/3. This greatly reduces the problem size. On the right of this slide is a video showing the full loading, holding, and unloading process during a 2D plane string simulation. We can see the initial loading stage, followed by the hold stage. We see that the load P is kept constant, but the indentation depth keeps growing, and we can see the development of the plastic string inside the sample. And finally, we can have a very quick unloading process. After the load is fully released, there's a post-indented residual geometry on the sample because the sample has undergone permanent plastic deformation. We can zoom in to the geometry of the residual indent, and it shows good consistency with what was imaged in real practice. The model is also able to capture the material flow during the indentation test, which is shown in the bottom figure. We can see that the bottom figure shows the scaled velocity for the sample during the test, and the sample is an isotropic sample with a bedding plane of 45 degrees to the horizontal direction. When the sample is compressed by the indenter, the material tends to flow from the stronger bedding plane normal direction from the stronger bedding plane normal parallel direction to the weaker bedding plane normal direction, which is shown by the blue arrows. That's the end of my presentation. Thank you.